Welcome back. This video is going to cover the rules on electron configuration and then the orbital diagram notation. So, if you're watching this video, most likely we've done the in-class activity with the boarding house model, and you've seen these things that we'll be talking about in this short video already, and this hopefully will just make it, maybe make a little bit more sense. But electron configuration, right, that is the arrangement of electrons in an atom, where they're located, and so on and so forth. Because where the electrons are located are very important for an element's chemical and physical properties. Because if you just look at the periodic table, and if you're just kind of looking at the periodic table, if you know anything about the elements and what have you, you just notice that the addition of one proton and one electron to an element can change it drastically. For example, if you go from helium, which has 2 protons and 2 electrons, you add another proton electron, now all of a sudden it's the element lithium, which is now a metal instead of being an inert gas, and so on and so forth. So you can see that where the electrons are, how many they have, and whatnot, make a big difference. So the first thing that you probably saw in the boarding house model activity was the Aufbau principle, which basically is saying is that the electrons will occupy the orbitals of lowest energy first. Yeah, you can also kind of see a diagram on page 156. This, in the boarding house model, remember, they filled the first level rooms first, and then moved on to the second, and then filled the sunny rooms, and then the pink rooms, and then only then could you go up to the third floor. That's basically just showing that the electrons are going to occupy the orbitals of lowest energy first before they go on to other things. Next thing to keep in mind is that the Pauli exclusion principle is saying that an atomic orbital may describe at most 2 electrons, and to occupy the same orbital, the electrons must have opposite spins. And we just refer to these spins as clockwise and counterclockwise. Again, probably mentioned during the thing is that we're not going to get too much into exactly what this spin represents, because this is a college physics chemistry topic, right? You won't get into understanding more about what actually the spin physically represents until you get to physical chemistry, if you ever take it. I know in the chemical engineering curriculum that was a junior level class at Purdue, chemistry 378. It was so much fun. But all you need to know for this sake of this course is just think of spin as clockwise and counterclockwise, and that they have to have opposite spins to share the same orbital. And the last one is talking about Hund's rule, saying that electrons will occupy the same energy, that they will not pair up in a sublevel that has more than one orbital until every orbital has at least 1 electron. Basically what this is saying is that they will not pair up unless forced. And you can see it here, where there's a little bit too many chemistry cats in that container. Another way to think about the Pauli exclusion, the Hund's rule, is, let's say that at home you have, you got some siblings and you got your parents, and let's say you have, let's say you've got a 4-bedroom home, and you and maybe you have 2 other siblings. So of your 4 bedrooms, parents are going to take a bedroom. That leaves 3 bedrooms. And if you have yourself and 2 other siblings, are any of you wanting to share a room with your sibling? Most likely, no. not unless you're forced to. So electrons are kind of the same way, that they're not going to share the same orbital unless they're forced. Now, in that case, and let's say you had a 3-bedroom home, or let's say your parents said that, hey, we need to keep one bedroom open as a guest bedroom, well, then you're going to be forced to pair up. I don't think there's actually a electron-like analogy to leaving a spare bedroom for guests, but hopefully that allows you to make a little bit more sense of kind of what Hund's rule is saying. So if we want to talk about orbital diagrams and whatnot, when we're doing this for an element, first thing we need to do is determine how many electrons are in each element. And right, you just have to remember to, when we're going back to filling out those tables and whatnot, is like, okay, or, since we're talking about neutral elements at this time, the number of protons and electrons are the same. So all you need to do is look up boron on the periodic table, right? That is the symbol B. And if you have your periodic table out in front of you, you can then just take a gander and see what the atomic number of boron is. And when you do that, I'll just sit here and wait. Oh, you left your periodic table at school? Oh. Okay, well, you could look it up on Google, right? Oh, that's too hard? Oh, all right, well, boron has 5 electrons. And if we want to place these 5, again, you see sunny, pink, pink, sunny, pink, sunny, pink. We're going to start with the lowest energy first, which are the lowest energy level, the 1. And so we'll put 2 there, because we got to fill all of the lowest energy levels first. And again, if you want to put, double-sided arrows, or if you want to put the first one down and the second one up, it doesn't really matter. That's all the same. So that's 2. We're going to put 2 here, and that leaves us 1. And right, we're going to have 1 in the 2p. And it doesn't matter if we put it in this box, or this box, or this box. And it doesn't matter if we put it facing down or up in any of these, because we only have 1 to put there. Right, so that's fine. The only thing that would make it wrong if you try to stick it here or here. Because if this electron was put in the 3s or the 3p, we would say that is an excited state. That this electron has gained some energy to be bumped up to the 3s or the 3p or beyond. Okay, but this electron being in any of these boxes, because it's the only one, or being up and down, is perfectly fine. Oh, looks like I've got a formatting issue. Got chlorine here, but all the boxes appear to be on the top of the next page. But while we're here, chlorine, right? The atomic number of chlorine is 17. So we will have 17 electrons to place up here. So I'll just rewrite this chlorine, right? And that is C lowercase l. We got 17 electrons. So let's start putting those suckers where they need to go. There's 2, 3, 4. This is going to hold 6, so that brings to 10. So this is going to be completely full, right? We just have to remember that those things. So up to this point, we've got 10 placed. We've got 5 more, so the 3s is going to be filled. That's 12. So we have 5 electrons to put here. P sublevel can hold 6. So that means we're going to have 2 of these boxes with 2 electrons and 1 box with a single. So it doesn't matter if I put these 2 filled ones over here, or this one, these first 2, or the one not, is that you are going to have something that looks like that. And this arrow could be up or down. It doesn't make any difference, because it's the last unpaired one in there. Nitrogen. Right? Nitrogen's got 7 electrons. So we'll fill the 1s, that's 2, 3, 4. We've got 3 to put here. So correct representations, well, you could either put it like this, all 3 being up, or all 3 being down. Both of those are fine, and would be correct. What you wouldn't be able to do is have, two, just have any paired up. That would not be acceptable, but either of these two are fine.